So the formula for a plane, and I'm just going to use my lovely three-dimensional graphing skills. So this is a plane floating around somewhere out there in space. And if I draw a normal vector to the plane, so this is introducing or reminding us of another vocabulary word. So if I say normal to, the same thing as orthogonal, which is the same thing as perpendicular. So when we talk about the normal vector to a plane, it is at a 90-degree angle with that plane. Well, what that means is if I find any vector at all that exists in this plane, then, and I'll just call that PS. So if that's any vector at all that exists in this plane, then I know the dot product between that normal vector and the vector in the plane is going to have to be 0, because the dot product of two vectors will always be 0 when they are orthogonal or perpendicular. So the way that we go about finding the equation here, so if I know that our vector normal to the plane is the vector 1, 4, 1, and I know that there's one point in the plane that I've been given, and let's say that that point is -1, 1/2, 3. And then I imagine a generic point on the plane x, y, z. So here's my generic x, y, z point. Then the vector between my generic x, y, z point and this other point here, I'll just call it v for vector. That vector I can get by looking at the displacement, or looking at the difference in location between where I'm starting and where I want to end up. So this vector, that I hat component, or the first component here, or a component in the x direction, is going to look like x minus -1. My component in the y direction is going to look like y minus 1/2, because that's the distance between the point we're at and where we're trying to get to. And then my k component is going to look like z minus 3. So there's my vector v. And I was using that phrase I, j, and k. I know that there have been some other homework problems. We just call, if I wanted to write this in the standard, using standard basis vectors, then that would look like x plus 1 I hat plus y minus 1/2 j hat plus z minus 3 k hat. It's just a different way of writing the same vector, but I'm going to stick with a row vector notation for now. So there's my v, and I've got my n, and I know that if I do n dotted with v and set that equal to 0, that's going to guarantee that my n and v vectors are perpendicular. And that's actually how we get the equation for the plane. So taking the dot product, I need to multiply my two I hat components, or the first components of the vector, together. So I'd have 1 times x plus 1. Then I'll multiply my second components together. So 4 times y minus 1/2. And then my third components together. So 1 times z minus 3. And set that equal to 0. If we had some time, we can multiply that out and make it look a little bit nicer. So that's x plus 1 plus 4y minus 2 plus z minus 3 equals 0. X plus 4y plus z is equal to, and then I'll move everything to the other side. So 1 and a -5. So it's a -4, and when I move it over here, it's a 4. I know this question didn't ask us to, but we could actually sketch what this plane looks like in 3D. So I'm going to get my axes going here. Here's my X, Y, and Z axes. So to sketch this plane, I'm going to start in a similar place that I would if I were sketching a line back in 2 dimensions, or R2, which is I'd go ahead and find the intercepts. When we find intercepts in 3 dimensions, we're actually setting 2 of our variables equal to 0. So if I set Y and Z both equal to 0, then my x-intercept would be 4. And if I set x and z both equal to 0, then my y-intercept will have to be 1. And if I set x and y both equal to 0, then z would equal 4. And I could go ahead and sketch the plane by connecting the dots. To give it a little bit of a depth, we can shade that plane in a little bit. Now, it doesn't just stop magically at these walls. Technically, our plane extends in all directions.